各位现场贵宾，让我们用热烈的掌声欢迎国科会吴成文主委莅临我们会场，欢迎主委。Ladies and gentlemen, let's give a round of applause for Minister Wu. Welcome, Minister Wu. Ladies and gentlemen, welcome to the Future Tech Pavilion FuTechs. FuTechs is co-organized by the National Science and Technology Council and other relevant ministries. This year, FuTechs is themed AI cross-disciplinary applications and innovative breakthroughs, showcasing cutting-edge research achievements from various fields both domestically and internationally, creating the most anticipated science and technology event of the year. 国科会吴主委，还有运动部黄启煌次长、中研院的陈君厚秘书长、卫福部的刘明勋技监，还有教育部的徐正邦副司长，以及呢我们现场的贵宾、媒体朋友们，大家午安，大家好。欢迎各位莅临由国科会携手中研院、教育部、卫福部及运动部打造的未来科技馆。那么今年呢，我们以 AI 跨域应用创新突破为主题，汇集了海内外各领域前瞻科研的成果，打造了全年度最让人期待的科技盛会。And today we are very delighted to welcome distinguished international guests to this grand event. And please allow me to introduce them and give them a big round of applause. First, our speakers for today's Smart Robotics Forum. Let's give a round of applause to welcome Professor Tamim Asfour from the Institute for Anthropometrics and Robotics for Koshiro at Institute of Technology. Welcome, Professor. And next, let's welcome Professor Atsuo Takanishi from Department of Modern Mechanical Engineering and Humanoid Robotics Institute at Waseda University. Welcome. Welcome, Dr. Stan Birchfield from NVIDIA. Welcome. Next, let's welcome Professor Karen Liu from Department of Computer Science at Stanford University. Welcome. Besides our speakers, we also have friends from overseas joining us. So if you are here, please stand up and wave to everyone. Once again, thank you for coming. Please give them a warm applause. Thank you. And next, we would like to invite our esteemed leader, Minister Chen Wen-Wu, to the stage for a few words. 让我们掌声欢迎国科会的吴成文主委上台为我们致辞。欢迎主委。
Good afternoon, all the distinguished guests, ladies and gentlemen. It's really my honor and privilege to be here to welcome you to this very important event, the opening of the FuTechs Pavilion. And I would like to thank Professor Yue Wenhong, the Director General of the Engineering Division for National Science and Technology Council, for organizing a very important forum for smart robotics this afternoon. And for this pavilion, I would also like to thank the partners of National Science and Technology Council, including the Academia Sinica and the Ministry of Education and Ministry of Health and Welfare and Ministry of Sport. So so you can see the demonstrations, the booths from all these partners all gathering here. It's very important, showing very important research results which can be realized and utilized for the industries and all sectors of the society. And I would also like to thank our distinguished speakers, including Professor Takanishi from Waseda University and Professor Liu from Stanford University and Dr. Birchfield from NVIDIA and Professor Fu from National Taiwan University and also Professor Asfour from Karlsruhe Institute of Technology. Thank you very much for joining us today. And I think all the audience gathering here are waiting for your very distinguished speech later on for the important forum of smart robotics. On behalf of the Executive Yuan of Taiwan, I would like to let our guests today to know that our government has formally approved a very important national program for smart robotics. And the program will be conducted by several ministries and councils in our government, not just National Science and Technology Council, but also Ministry of Economic Affairs, and Ministry of Digital Affairs, and Ministry of Health and Welfare, and Ministry of Agriculture, and so on, so many education as well. So many ministries joining together for the benefit of the society, of the people, to develop industries that can help serve people for the future. So the emphasis of the smart robotics program for our country will be focused on service robotics. Service robotics for all kinds of services that the humanity, for all kinds of humanity needs to serve all people. For service robotics, we emphasize not the original robotics industry, which is for manufacturing, but we emphasize AI and how to transfer human knowledge, human intelligence to the machine, and then can deal with all kinds of needs that can serve people. For even disaster prevention and recovery, which we have just encountered in Hualien the past few weeks. And for saving lives, for helping people to prevent even traffic accidents, to serve very dangerous works that originally done by human beings, but it's too dangerous so that we can use machine to do the jobs. All kinds of needs for the society is the main purpose for the National Robotics Program. So we would like to emphasize very innovative AI-enabled applications and systems and services to help human beings. So for that purpose, we are integrating all different expertise to help come up with systems, not just components. So in Taiwan, in the past, we focused on the manufacturing side, ODMs and OEMs industries, EMS industries. However, in the future, based on the existing hardware manufacturing expertise that we have today, we would like to invite international collaboration partners so that we can develop smart systems that can help people, as I mentioned. And for that purpose, we need to collaborate with so many different partners from all over the world. That is why we have this forum in the afternoon, this afternoon. And we also are showing different research and technology, scientific research and technology development results in this event in the next few days. We also invite everybody to take a look at them because that shows the results from different ministries and councils. They invested in science and technology in the past few years and showing the result here. So we also invite our international visitors here to take a look to see how Taiwan can collaborate with you together to make the world better in the future. So once again, I would like to thank everybody to join us today. And I hope that for all the visitors today here, you have a very wonderful day and fruitful event in the next couple of hours, listening to the speeches of our distinguished speakers here. And please enjoy the show. And I hope everybody can have something that you can take away to make Taiwan and the entire world better in the future. Thank you very much.
Thank you, Minister Wu, for the inspiring remarks. Please have your seat. 感谢主委的致辞，请主委先回座。Today, we are very delighted to have our distinguished guests from abroad and from various sectors join us to witness the pioneering technological outcomes at the Future Tech Pavilion. And next, we would like to invite our guests to the stage for a group photo in the following order. 我们今天现场有来自许多远道而来的朋友参与，那么难得的机会呢，有产官学研界聚集在未来科技馆。接下来呢，我们要先来进行今天的大合影。首先呢，让我们要邀请到国科会吴成文主委，继续要邀请国科会苏正刚副主委。接着要邀请科技办张正豪执行秘书，继续要邀请中研院陈君厚秘书长，继续要邀请卫福部刘明勋技监，接着要邀请教育部徐正邦副司长。And next, we would like to invite our distinguished forum guest. Let's welcome Professor Tamim Asfour. Welcome. And Professor Atsuo Takanishi. Welcome Dr. Stan Birchfield. And Professor Karen Liu. And Professor Li Chenfu. 以及国科会工程处的洪岳文处长。好，我们请各位贵宾看向正中间挥手的这台相机 ，Please look towards the center camera. And one more photo, maybe we can make a thumb up gesture， 比一个大大的赞，给我们的未来科技馆。好，我们摄影师 OK 吗？好，接下来呢，我们邀请第二阶段的合影贵宾上台。首先欢迎产学处林德生处长、竹科管理局胡世明局长、中科管理局许茂兴局长、南科管理局郑秀荣局长、前瞻处蔡妙慈处长、资讯处周子元处长、自然处赖明志处长、人文处黄俊如处长、科国处李旺龙处长、生科处涂君怡副处长、国家太空中心吴宗信主任，以及国家灾害防救科技中心陈宏宇主任，还有国家同步辐射研究中心徐家宏主任。 好，我们要再次邀请贵宾看向正中间挥手的这台相机。Please look toward the center camera. 好，我们一样，第二张比一个大大的赞。Please make a thumb up gesture to the camera. And one more, please look your left side this camera. 好，我们还有媒体朋友们需要捕捉的吗？Your right side. 好 ，OK, please look at the center again. 好，我们现场摄影师都 OK 了吗？那我们再次的感谢我们台上所有的贵宾。Once again, thank you for our distinguished guests. Please have your seats. 好，我们再次感谢今天与会的长官贵宾们的莅临。紧接着呢，我们要进行的就是现场来宾们呢非常期待我们的智慧机器人论坛。我们的开幕论坛活动呢将聚焦在智慧机器人发展趋势。那么第一场主题演讲呢，我们非常的荣幸邀请到人形机器人领域的国际权威。那么他所领导的团队呢，开发出了可以在真实环境中与人协作的人形机器人。今天呢，将为我们带来的主题是人形机器人迈向通用型智慧的未来。Now we proceed to today's opening forum, and today's event focuses on trends in intelligent robotics. So for our first keynote, we're honored to invite an international authority in humanoid robotics, Professor Tamim Asfour. Let's give a word of applause to welcome Professor Tamim Asfour.
Yeah, good afternoon, everybody. It's an honor and pleasure for me to be here. Thanks a lot for the National Science and Technology Council for inviting me and for giving me this opportunity to learn about Taiwan, about technology in Taiwan, about the motivation of young people working on smart robots in Taiwan here, and for the REACH program, what the organizers put together to give us an idea about robotics and AI research here in Taiwan. So in the next 20 minutes, I will give you a brief overview about why I think humanoid robotics is so important for our society and for our economy. As you know, robotics is everywhere. Robotics is changing the way how we work and how we live. And if you see here in these examples, robotics in production, in exploration, in construction, agriculture, in medicine. But if you look at these systems, every system has been developed in order to perform a task in a perfect way. A robot for production cannot do agriculture tasks. A robot for logistics cannot do medical robotics tasks. And this is what we would like to change with humanoid robotics. Humanoid robotics are versatile machines. This means these are machines which are able to perform a wide variety of tasks, and one day, any task what a human can do and maybe better. And the goal of our research is actually to understand the versatility of the human body and the motion intelligence of the human body. Why are we as humans so performant and can do so many things with the same embodiment, and why we are still not able actually to build technical systems in form of humanoid robots which can do the same. So we are interested in building general purpose machines which can perform any task what a human can do in order to improve and to contribute to a better quality of life of humans. And in the last year, I added the last item point on this slide, which I have been using in the last 25 years. Humanoid robotics is a multi-trillion market. Projections tell us that the market of humanoid robotics in 2035-40 will be as big as the market of automotive. what we are doing here, I have been working in this field since 25 years. These are the humanoid robots we developed at the Karlsruhe Institute of Technology in Germany. And in order to provide help and longer self-determined life for people at home. So you see here our labs, a kitchen environment where the robot should help anybody, any person in daily activities, provide versatile and personal assistance for humans at homes, but also for caregivers, for example, at nursing homes, hospitals, retirement homes. I will not go too much into the details of the research questions, but I would like to show you some examples. Some examples of the work we are doing. So you see here a humanoid robot performing tasks in a kitchen environment, like loading the dishwasher, cleaning the table, or a humanoid robot helping a human to prepare dinner for two people, as you see on the right side, where the challenge is to map this natural language instruction, Amma, please help me to prepare dinner for two people, into motor actions. To have a robot which has an understanding about its own abilities, about the tasks, what it can perform, and the task which should be done by the human, for example. Since the robot cannot cut the salad, the human should cut the salad, but the robot can wipe the table, can pour the oil, and so on. And recently, we arrived at version 7 of our humanoid robots here. And the goal of this AMA Robot 7, the 7th generation, is to provide assistance for caregivers in retirement homes. So where I believe, in particular in Europe and in Germany, this is a very severe problem and labor shortage in the area of healthcare. And therefore, I believe here that humanoid robotics can provide a solution or can provide a sustainable solution for these societal challenges. So it's not only about building these systems, about the mechatronics of the systems. You see here additional cognitive abilities of the robot or sensory motor abilities of the robot. Robots at home should be able to deal with any object, to manipulate any object, anytime and anywhere. And you see here the abilities of the robot to handle deformable objects, but also to recognize the intention of the human in the context of handover tasks here, as you see here in these videos. It is not only about developing the hardware and the operating system behind it, which is really challenging and which we have to master in this area, but it is about building the architectures behind these hardware, behind these machines, which allow us to understand natural language, which allow us to understand situation based on visual information, and to map instructions like help me to prepare dinner for two people into motor commands. And we believe here in this context that these architectures should be memory-centered, and that the memory system in the human body or in the human brain is very crucial and very important. And this is why we started implementing a memory system for our cognitive architecture, in particular implementing a deep episodic memory with deep neural networks, which allow us to encode the experience of the robot and to recall this experience in a very efficient way in order, for example, to verbalize to humans something about the past of the robot. I'm not going too much into the details, but this is how maybe this architecture works. The robot would collect everything what it perceives, the objects it perceives, the names of the objects, when it perceives or detects an object, how it grasps an object, how it manipulates it, where to place it.
Can you please tidy up while I'm away?
You see here an example. I will be away for a few minutes. Can you please tidy up? And the robot knows how to perform this task because it has plans which we encoded, for example, which was learned by the robot, and then the robot stores all camera images, the information about the objects we grasped, and so on, in order to be able to answer questions like, did you see the red cup? Yes, I last saw it on the table 10 minutes ago. Sorry. You see here how this episodic memory is built, and now Leonard is back.
Tell me what you did, please.
I moved a multivitamin juice to the countertop.
How long did it take to grasp the green cup today in the afternoon?
It took about 1 minute.
Tell me which object you moved to the countertop yesterday at 2 p.m.
I moved the red cup.
When did you last see the red cup?
I saw it on December 9th at 14:56.
So this is a very simple example, and this is what we expect actually from robots which should act or should help us at home to be able to answer these questions. If we look into the data, what we need in order to build these models, our robot generates about 350 gigabytes per hour. This means about 3.1 petabyte per year. Of course, we are not using only the raw data, but latent representations of the data, so representations in smaller dimensional spaces. But though also in these spaces the data remains significant, and this is why we are investigating how mechanisms of forgetting what we know in humans can be implemented in order to build episodic memories for robots which are as efficient, as performant, maybe at some point, as human memory systems. So the next example for humanoids, and humanoids are general purpose machines, is actually to help humans in 3D jobs, or actually to replace humans in 3D jobs, in difficult, dangerous, and dirty jobs. And you see here some examples with the 6th generation of our robot, where on the one hand, the clicker is, on the one hand, the robot is able to support or to assist a technician in repair and maintenance tasks. The robot is able to recognize when a human is in need of help based on the task information and based on the interpretation of the current situation. For example, all these tasks are tasks which require 2 people, as you see here, like lowering the guard, like setting up the ladder for the expert technician in order to inspect the conveyor belt from the top, or like placing the cart here at the right position with the tools which are needed for maintenance and repair tasks. Another example of dangerous jobs is decontamination of nuclear plants. And you see here how these decontamination tasks are done these days, where a human has to pick up objects in a box to clean them and to place them in another box. And we would like to remove this human from this environment. Yeah. And you see here how our robots are able to grasp and to manipulate difficult objects. This is about grasping of unknown objects in cluttered environments, and where the robots are also able to recognize failures and to recover from failures. I have to hurry up. The second part, what I am going to talk about, is how our robots learn from human observation. And since I'm running out of time and people are giving me signs from the back that I have to stop in 1 minute or 2 minutes, I will skip many of these exciting things where we collect data about how humans perform tasks, highly accurate data, and data about the motion of the human, but the motion of the objects, and where we can, with machine learning methods, segment these human demonstrations in elementary actions, which we call movement primitives, which can be used in order to implement complex tasks like prepare the dough, for example, or like cleaning the table. let me skip this, how we learn actually these sparse representations of manipulation tasks based on visual information. Yeah, you see here, for example, the pouring task can be represented by very, very few key points of the demonstrations, which can be used in order to generalize to pouring in different cups and from different containers. You see here how this can be done also with very, very few number of demonstrations. So only 6 to 8 examples are needed in order to have the robot learning these bimanual coordinated or tightly coupled or loosely coupled manipulation tasks. Humanoid robots made progress, and we see a lot of new systems these days. The whole thing started at the Waseda University with the Wabot 1 humanoid robot. And I need the next slide. And the question is not actually whether humanoid robots will be part of the society, but it's about the when. And we have, I see, 4 undeniable forces. The progress we are experiencing in AI, that we are able to manufacture these robots, so mass production is happening now, what Tesla, Figa, Unitree are doing. Aging population and labor shortage, there is no other alternative for a solution, and the form factor wins. So our entire infrastructure is built for humanoid robots. And I can tell you, that some people in the room might doubt now and think what's Tamim telling me, but let me give you a few examples. 95, people said internet is a fake. Nobody needs a smartphone in 27. AI cannot understand language, 21. And today, humanoids will not work. And you see here that actually the history is on my side. The history is on my side, and the data, they are always wrong. Yeah, we had all these things. So the next revolution is the fusion of humanoid robotics and AI. And with that, I have to stop here. Thank you for your attention.
Thank you, Professor Asfour, for your wonderful speech. Thank you. Please have your seat. And for our second keynote, we'll present humanoid robotics research and its application. We are honored to invite Professor Atsuo Takanishi. Let's give a warm round of applause for Professor Takanishi.
Hello. My name is Atsuo Takanishi from Waseda University, Japan. And, okay, how can I fast forward? Okay, first, she's from Taiwan. She's my postdoc, a very good collaborator in my lab, doing a research on human robot like this, musical robots, for long years. So this time, she even helped me a lot. And she's also a PhD student. She's Japanese, and she's making a sort of pitching robot. So you can see the video. I hope it works. Like this, very fast. Have you ever seen this before? In this case, the robot is not only using actuator, but also using a spring and its mass. So it's a sort of human how to perform the energy efficient motion. This is very, very important, I believe. And she's good to see. She's a Chinese, and she also, he helps me a lot about doing research on not only human, but also exoskeleton or leg prostheses, intelligent ones. And by the way, he is the first guy who started human research in history. Professor Ichiro Kato, my advisor. So unfortunately, he died in 1994, but he developed many types of humanoid. But these two robots are very famous. Robot 1 stands for Waseda robot number 1, and the second Waseda robot number 2. The first one was built in 1973. That time, the speed is very slow. One step, 45 seconds or even 1 minute. And the step length was only 10 centimeters. But at that time, this is the first time in history the robot walked by itself. The second one is not working, but playing a keyboard like this by reading a musical score about 1 meter away from the robot head. Okay, why humanoid robot? Professor Kato told me that making a human robot is knowing a human self from the viewpoint of engineering. This is a very important viewpoint. That's why we have been making human robots for long years. And the second one is robotics, one of the social technology based on the human model. So after this, so we have a lot of models about the human self. So our design methodology can be based on that model in terms of engineering, I believe. So the second one is the making of human robot is a sort of grand challenge. So when I was an elementary school kid, so I watched television, the American astronauts standing on the surface of the moon. That's a big shock to me. So after that, I more entered to science and technology. And after that, I made a lot of different types of human robot like this. Okay, this is Wabian 2. But anyway, this robot was built about 20 years ago. But you can see the robot has a special pelvis mechanism. Nowadays, many robots are using that configuration. But at that time, no robot other than this has such kind of DOF configuration. And also, the mass distribution and the length of the limb system are almost same as human anatomy. So I still this robot is the most human-like humanoid robot in the world. And you can see that the robot, I hope. Okay, this robot can fully extend the knee while walking by using the pelvis motion. This is the same as how human is walking. So extend the knee is energy efficient walking than the robot like this. And also this robot can walk outside like this. Very smooth. And the important point about human science in terms of engineering is this. So human has two peaks while walking. The floor reaction force in the vertical direction. So other apes, chimpanzee or gorilla, has only one peak. So this is a big difference between human and the other type of apes. But for example, the Wabian 2 has really two peaks, like humans, while Wabian walk like this, like Ashimo's walking or something, always bending the knee. So this is a big difference. So by humanoid, we can confirm how human is moving. And also we make the foot more smaller than like human, like this. And also human robot can be used as a dummy robot. So in this case, at that time, Hitachi was developing a sort of a system. So in the end of the stage, they want to use apply to human, but still they are afraid of some injury. So they ask us to use our humanoid robot in order to replace the human with the human robot. And also human robot has so many sensors. So you can easily obtain many data if something happened, fall down or even falls working. And also, my university has a human science department. We also collaborated with them. We first measure the human motion. He's a handicapped, and one half of the body doesn't move, but we try to move the data to human robot like this. And also, okay. Oops. Okay, anyway, the society needs to change the law. This is very important. In order to accept those high technology to human society. So we especially applied to the government, change the traffic law to allow a humanoid to walk or run in the public road like this. We did in the Fukuoka prefecture. By the way, Fukuoka is where I was born. Okay. Okay, we also collaborated with the European collaborator like this, Professor Paolo Dario, Alan Bertos, and many other research groups. And our technology also, not only within university, but also to distribute to companies like, not only companies, but also other governmental organizations, METI and TEMSAC, and even Sony. We collaborated and we give them licenses. And also now, like Minister Wu mentioned about disaster. This is the same situation in Japan. So from the 2015, we did a sort of collaboration research within Japan. And this is one of my the research laboratories alumni, Professor Hashimoto. Now he's a full professor of Waseda too. So he made this kind of robot because he developed many human robot before. Now he is trying to make a disaster robot like this. And this is a sort of armor in order to protect the robot itself. And this is the most important part, the actuator. So we collaborated with Mitsubishi Heavy. They supplied us a lot of know-how how to make actuator. So at that time, we had a sort of small line in university, and we developed many different types of actuator like this. And just 2 weeks ago, we press released the new organization called Kyoha. So because there are many good companies located in Kyoto, so the companies organized the new organization to really develop useful humanoid. And at that time, there are several industry. This is totally industry-driven project. And now many companies are asking us to join. And very sorry, only in Japanese. But, I don't have time to translate to English. But like this, many parts of the robot can be supplied by those Japanese companies. And one of the most important applications is disaster. Because Japan is maybe the top in the world, having many different types of disasters. So the first thing that we have to concentrate on is this. By the way, like pitching robot, this robot is running like this. using of spring mechanism. So this is this kind of motion can be energy efficiently done by using this kind of mechanism. And also my young colleague, Professor Otani, and also one of my young alumni developed this kind of two-leg chair. Because in the real environment, wheelchair cannot be used sometimes, like steps over here. So if the chair has this kind of two-leg mechanism, so you can go up, down the staircases like this. And this is also collaborated with the Japanese company, Temsa. Okay, and it's something like 20 years ago. But we moved this robot to Los Angeles. And there are many people get on that robot. He was a mayor of Los Angeles. I don't know if he's continuing the mayor. Maybe in the US it's impossible. And okay, this is my collaborator in research, musical robot. I hope this robot can, okay, you can enjoy the robot playing the flute. This robot has two lungs, like humans. So this robot needs to breathe in order to continue the play. And you can see the lip, depending on the tone, the lip shape changes in order to make optimal sound. So that methodology was learned from a professional flutist. Okay, this is a saxophonist robot. Okay. By the way, this research is done by a German student. Now he's because he's a semi-professional of the saxophone player, so he made this robot. Okay, next robot is speech production robot. This is a collaboration with NTT, Japanese telephone company. So they want to have this kind of robot in order to do research on how human is producing speech. I hope you can see, this is Japanese vowel, a, i, u, e, o. This is volume up, please. Okay, if you access to my lab webpage, you can listen to the different speech by this robot. But anyway, speaking of human speech was very, very tough. So you can understand how human is, very greatly produce many types of motion like this, performance. You need to be airtightness. This is very important. So this is IUL, the other types of speech production. So very, very hard to listen, but we just do that. And this is not a speech. This is a sort of drinking. Okay, this is a more, mental-related human robot. Okay. The important thing is equations of emotion. So we need a sort of equations in order to control robot precisely. But we believe that there should be a sort of equation for emotion. So this is our idea. After that, the robot perform like this. In the beginning, the robot sees a rainbow. Robot expressed the happiness, but the robot has many different sensors on the body. If you hit, the robot react almost real time, and the robot has two microphones in the middle of the ear, so robot can localize the sounds. And also, whenever robot sees the red ball, robot was abused. The robot becomes angry. But if the robot smells alcohol, in this case vodka, robot becomes happy because the robot is drunken. But this robot has a similar lung system. So gradually robot becomes serious. Then, so this is a sort of how this kind of emotional robot reacts to the environment. And okay, I should skip. Okay, now we combine the emotion extension robot and the Wavian 2. And you can see some gag.
続きまして、びっくりした瞬間のマスオさん。
Anyone who likes this very short gag? And this is another type of.
芝刈り機の真似。
Something like this. By the way, we, before the Corona pandemic, we collaborated for something like 10 years with the theater players. So the human robot can be useful for theater play. You know Osamu Tezuka? In Japan, he is a god of manga. And the one theater group is playing some of his manga in the theater. So this is so it is impossible by human to mimic like this. Okay, he's a director of the theater play group, and we taught them how to make a robot. So now they make this type of robotic mechanism by themselves. And now I'm in some kind of a collaboration research center called Twins. It's between Waseda and the Tokyo Women's Medical University. Okay, this is a very old research, but working together with dentistry people, something like 40 years ago. So I developed this kind of chewing robot because they want to analyze human chewing motion without using human, because it's a breaking of time up. Okay, sorry, I have to end. But like this, I have been doing a lot of human robot research like that. So I hope everyone here enjoyed a lot, and in the future, Japan, Taiwan, Japan has some collaboration in terms of human robot like this. So we have a lot of application like that. Thank you very much.
Thank you, Professor Takanishi, for the wonderful speech. Thank you. Please have a seat. And for our third keynote, we're honored to invite Dr. Stan Birchfield from NVIDIA, and he will present 3D scene awareness for robotic manipulation. Let's give a warm round of applause for Dr. Stan Birchfield.
Hello, everyone. Is this on? Is the microphone? Okay, there we go. Hello, everyone. Get back. Okay, so we all want robots to do useful tasks for us, like make a cup of coffee. And I used to start talks like this by asking the question of whether we were really making progress. Because from one point of view, a decade of research and the systems look kind of similar. But we have entered a new era, as you know. So I don't think that's the question anymore. We now have huge advances in hardware and software in just the last couple of years, so that we now have robots making coffee, but in a fundamentally different way. So now I think the questions are, are we done, right? Is this the end of the research? And if not, what is missing? So I'm going to propose that we need, among other things, 3D scene awareness. So the robot needs to be aware of its surroundings. And this is necessary to make sure that robots act safely, to make sure that their actions are interpretable, and also to deal with the data scarcity problem. So when we first started looking at 3D scene awareness about 10 years ago, we started with the problem of object pose estimation. Oh, is this? Okay, so about 10 years ago, we started looking at object pose estimation, and this led to the work on DOPE, which is deep object pose estimation. So we have a deep neural network. It processes an image and detects all the instances of the object, and as well as getting the 6D pose, which is the translation and the rotation parameters. And the output of the network is then fed to an off-the-shelf PNP algorithm, and this algorithm is robust to pose, occlusion, lighting, and so forth. We trained the network solely on synthetic data. We found that a mix of domain randomization and photorealistic data achieved the best results. We need synthetic data because it automatically gives us perfect 3D annotations, which is very hard to do with real data. And with that training, our network was then able to achieve state-of-the-art results, right, compared to previous works, and it was able to deal with extreme lighting changes, extreme poses, upside-down objects, and so forth. We then, so anyone in the world could download our code, they could run it in their lab, but only if they had the same objects that we had, and this is a problem, so we wanted to make it possible for anyone in the world to use our algorithm on their objects, and so we came up with this HOPE data set. We found some toy objects, we scanned them, the synthetic rendering is shown here on the bottom, and then we trained the model on all these objects, and so then anyone in the world could download our code with the pre-trained model weights, and they could also purchase these objects online and then do physical experiments in their lab with our code. So we're all about trying to enable other people to do their research, and so this is one of the early successes that we had. So DOPE solves the model-based problem when you already have a CAD model at training time. So you can train the network to work on that specific object. But what if you don't have that? We want foundation models. So a foundation model would enable you to do object pose estimation when you don't have the model at training time, only at test time. So this falls under the category of model-based tasks. But we also want to do model-free tasks. So if you don't have a CAD model at all, we want to be able to do 6D object pose estimation if you have a set of images of the object. So you can do static onboarding with the object sitting still on the table, or dynamic onboarding if you have the object, say, in your hand, for example. And this led to the handle data set. So we took a set of real objects, hardware tools, and kitchen instruments. We used a NERF-like process to do multi-view capture of these objects, and that enabled us to get very highly detailed, accurate 3D pixel-wise segmentation of these objects, as well as a segmentation of the handles of the objects for object affordances. And so our goal here was to support things like functional grasping. Both of these data sets, the HOPE data set and the handle data set, have been incorporated into the BOP Challenge. So we partnered with the organizers of the BOP Challenge, the benchmark for object pose. And our data sets support not only the model-based tasks, whether the objects are seen or unseen, but also the model-free tasks. So here we're showing the dynamic onboarding sequences of one of the HOPE objects. This led to our work on foundation pose. So this is a foundation model that is able to perform 60 object pose estimation on objects that it's never seen before at training time. So it handles it handles the model-based case, but it also handles model-free. So it'll also work if you don't have a CAD model at all. And it works on single images as well as videos. So it actually solves 4 different problems under the category of unseen. And as you can see here, we achieve state-of-the-art results on all 4 of those problems. So this is a render and compare algorithm. So at the bottom, you see the input image, and then we render the CAD model at a particular pose. And then we can do this in parallel on a GPU for a large number of hypothesized poses. And then it runs through a 2-stage process. We have a pose refiner followed by a pose ranker. The pose refiner is a Siamese network. It takes the input crop as well as the rendering, and then has some additional layers followed by transformers that output the delta rotation and delta translation to refine the pose. And then we do this in an iterative process until it converges. And you can see it runs again in parallel on all these different poses to refine the hypotheses. And then the pose ranking network will take the output of that and perform a global assessment of all the poses that it sees in order to determine the absolute, or determine the ranking from which it chooses the best pose. Okay, so we trained this model also on synthetic data only. So we use the Objaverse CAD models, and then we use LLM to add diverse textures to these objects, which enables a large-scale training data for training this network. And we were able to achieve first place on the BOP benchmark. And so we're still the #1 open source method on this benchmark. So you can go to our website, download our code, and you can use it in your lab. Okay, so this is an example of foundation pose running on a video sequence. So these are the YCB objects, and you can see that it does a good job of tracking these objects over time, even when there's severe occlusion. So if you notice the can behind the yellow mustard, even though it's severely occluded, we're still able to track it. Okay, so what if you don't have a CAD model? So this is where our bundle SDF system comes in. At the top, you can see the input video sequence. We also have, we assume that you have a mask, a 2D mask of the object in the first frame. And then this is a SLAM-based system, so it simultaneously estimates the pose of the object in each frame, as well as performing a 3D reconstruction of all the pixels that are not occluded. So here, okay, so here are some example results. You can see the high fidelity that it achieves in preserving accurate geometry, the legs of the table and the flatness of the table and so forth. It only reconstructs the pixels that it has seen. So in some of these videos, the person does not regrasp the object, and so some parts of the object are never revealed. And so we're not doing any hallucinating here. But otherwise, we will be able to recover the entire geometry. Okay, and we're a research group, but we partner with our product groups at NVIDIA, and sometimes they will take our code and they will extend it and make it even better in various ways. And so this is an example of the Bundle SDF commercialized version of Bundle SDF, in which case they have extended the code to make it better able to handle transparent objects, reflective objects, symmetric and deformable objects, and so forth. So you can go here, you can download the code. Again, you can use it in your lab, not only in a research lab, but also for commercial purposes. Okay, so we can take this Bundle SDF and we can plug it into Foundation Pose. And so instead of requiring a CAD model, even at test time, we can then take a set of reference images, produce an implicit representation of the object using a NeRF-like process, and then using neural-based rendering, use that to replace the CAD model rendering inside Foundation Pose. Everything else remains the same. This enables us to run Foundation Pose on an object that is never seen before. So this object, we take a few reference images to perform that bundle SDF computation to get an implicit representation of the object, and then we can track the object over time, even though it doesn't have a CAD model. Here's another example of Foundation Pose doing model-free tracking on a set of objects that is never seen before, other than the reference images. Okay, and of course, there are many applications for this type of technology. So you can imagine augmented reality, where you can turn objects into games and so forth. But our real interest is in robotics. So this is a research project we did recently where we took Foundation Pose and applied it to human demonstrations in order to track the object that in the context of a task that the human was performing. And we also track the target object as well as the source object, and so we can get trajectories in a common coordinate frame, which we can then use to train a diffusion policy, and that enables the robot to perform tasks that were presented to it by human demonstration. So here we have, for example, pick and place tasks where there's a source object and a target object, and we want the robot to be able to manipulate them in certain ways according to the demonstrations. Okay, we can do peg and hole as well, insertion using Foundation Pose. So here we have a plug and a socket. We're tracking both of them using Foundation Pose and using that to perform the task. Foundation Pose can also be used to overcome the data scarcity problem. So here we have human demonstrations. Foundation Pose enables those demonstrations to be pulled into a simulator, and in the simulated world, we can then generate variations on the theme, and that enables us to have much larger training set than we would otherwise have. And then once we've trained the policy, we can then apply it to the real world because we have Foundation Pose matching the sim to real. Okay, but we're not only interested in object pose estimation, we also want to get a full 3D reconstruction of the environment. So some of our recent work is in that area. We recently revisited the classic stereo problem where you have a left and a right image, and you want to match those images in order to get a dense pixel-wise depth map or disparity map. So if you'd asked me a few years ago, if you'd shown me an image like this, I would have assumed that it was the result of some sort of ground truth process, but this is actually the result of our algorithm. And you can see, again, the high detail, the fidelity, and, again, the denseness. So we're getting a result for every single pixel in the image. Compared to RGBD sensors, as you see on the left, our method on the right is able to do a better job of handling reflective surfaces and dark surfaces, and we also do a better job of preserving flatness of the table and that sort of thing. And again, here you can see the straightness of the lines and the 90-degree angle of the Kleenex box, and also the curvature of the mug and the handle and so forth. So again, much higher fidelity from a passive stereo algorithm. So the Foundation Stereo, it's a deep neural network. We leverage monocular depth estimation, and then we fine-tune that, or we really adapt it. We adapt the monocular depth estimation in order to make it applicable to achieving metric depth estimation. And then after the matching, we have some follow-on blocks, conv-GRU blocks that are able then to refine the disparities to get the final output. We, again, train it only on synthetic data. So this is some examples of some of the data. And we achieved #1 on both the Middlebury and the ETH 3D data sets, or the benchmarks, the worldwide benchmarks. And again, our method is still, even though it doesn't look like #1 here, it's the #1 method for which there's open source code available. So again, you can download our code, you can use it in your lab. Okay, so there are lots of robotic applications you can imagine using Foundation Stereo for. This is, again, the result of our algorithm, object to camera pose estimation, and so forth. We're also partnering with Meta. So they, with their Aria glasses, they're using Foundation Stereo to achieve depth estimation, and they're going to be talking about this more next week at the ICCV conference. Okay, well, I've lost control of the display. We're using Foundation Stereo and Foundation Pose in a lot of different research projects, and we're also partnering with companies that are doing like bin picking and that sort of thing. So you saw some of these images and videos flash up here. Hopefully you can kind of make sense of them. We're also doing indiscriminate grasping and so forth. We're also interested in VLMs. So VLMs are notoriously not all that great at doing 3D queries. So if we want to know where an object is in 3D, we need to fine-tune the VLM on data with that information in it. And so here, so our recent CVPR paper this year, we presented a data set called RoboSpatial that we used to fine-tune the VLM in order to get 3D, to do a better job of handling those 3D queries, answering the questions like where an object is and so forth. And so here you can see an example where we plug that into a robotic system. We're interested not only in perception, but also in control. And so we have a QRobo. QRobo is our online motion generation system that avoids collisions. It's a collision-free generation system, and you can, again, download this code, and you can use it in your robot lab. We avoid collisions by modeling both the robot and the obstacles using spheres. Makes everything fast. This is QRobo running on a real robot, following a sequence of desired poses. We can run this on an embedded GPU in real time. And well, there's more research involved. Okay, but all of that requires us to have a full 3D reconstruction of the environment, and so we have done some work on that, and this is still an active research that we're doing. And so just trying to show you, like, for example, some of the results that we can get using our 3D reconstruction algorithm. And I'm almost done. The final thing I wanted to show you is just that we're working on a new version of QRobo. It's going to be available to the public soon, so stay tuned. It makes it easy to add cost and constraints for avoiding like interpenetration and making smoother motion and so forth. None of this would be possible without our amazing researchers in my group, as well as our interns and collaborators that work with us. So shout out to them. 3D awareness is crucial for robotics. I've listed shown you a bunch of tasks that sort of fall under the umbrella. Neural reconstruction is super powerful. We have found that synthetic data is able to achieve the sim to real transfer immediately on some applications, and we predict that that'll continue in the future with more applications. And foundation models are here. And just to reiterate that our software is available both for research and commercial use in many cases. So if you can't find what you need, let me know and I'll try to help you connect to the right person. Thank you very much.
Thank you, Dr. Birchfield, for your wonderful speech. Please have your seat. And for our fourth keynote, we're pleased to invite Professor Karen Liu, who will present the new frontier of psycho-intelligence in humanoid robotics. Let's give a round of applause for Professor Karen Liu. Welcome.
All right. It's my great honor to come back to Taiwan to give a talk talking about my favorite topic, humanoid robots. And the best thing about being the last speaker is the question has already been answered eloquently by our previous speakers. Why humanoids? I think I'm just going to skip that, and everybody's on the same page now. A more interesting question to me is why now? This is definitely not the first time people are excited about humanoids, right? We have seen a lot of hypes before, and they just died out eventually. What makes this time different? All right, next. That's what they told me to do. Is this the answer? It's because of AI this time around, humanoids will stick? Well, I think that answers parts of the question, but to me there are other arguably more important factors at play. A lot of people would say high-density batteries, high-performance electric motors development in the last decades, they are game changers. But there are a lot of other often overlooked factors or enabling technologies, such as 3D printing, very cheap 3D printing, free online design tools, customizable PCBs, and just the cheap but still powerful on-device compute. All these new advances create this very welcoming environment for robot hobbyists to tinker, to iterate, to design, to develop robots very quickly and cheaply. And because of that, you know, we in the last few years, we have seen a lot of hobbyists become startup founders. And this collective energy and momentum is why it's driving humanoids industry today. And I think that's the reason this time around is different. So what is our vision? We recently developed an animation system that can conceptualize our vision very well. Next. So this is a digital agent, but it is fully physically simulated from head to toes, including all the fingers. And this agent can see the world, see this virtual world, and it also understands high-level natural language commands. So here we ask the agent to set up a workspace, and the agent will come up with a plan and figure out what important objects to interact in what order. And for example, you put monitors on the desk, it knows that it has to face outward, not facing the wall. And we don't need to tell this agent to do any more details planning. It will figure out everything on itself because it is connecting to a large language model, actually VLM in this case. And we can ask agent to do other things. This is a long horizon task. Ask agent to pick up the shoes, to do laundry, and that's it. You know, that's just sort of an autonomous agent we want to be able to realize in the real world. So that's our vision. And eventually, what we want to build next is a humanoid policy. And I think this is something that a lot of people share, this vision. We wanted this one policy that can do navigation, manipulation, locomotion from egocentric vision and human level natural language. Next. So how do we achieve this vision? Our bet is that we are going to solve the robotics problem using computer animation. And this is the best bet because this is the bet I know the best. My background is in computer graphics and doing animation. Next. So for example, in the past 2 decades, we've been building a lot of human digital agent models that can condition on interesting input modality. Like in this case, it would be audios, and input would be audio, output would be the human motion. Next. And during this exploration as a computer graphics researchers, I realized 2 things are really important. The first thing is not just the motion that we care about. We care about the interaction with the world. And also we want our motion to be physically generated. So what you're seeing here is not just a sequence of poses, it's a sequence of joint torques. And then we use physics engine to realize the kinematic motion. Next. So this is what we could do in computer animation today. Next. So it sounds like if we can already physically simulate a digital agent, all we need is just push to the real world to do sim to real. So we have, can we go back to one slide? Yeah, so between human motion, between computer animation and humanoid policy, there are 4 really important gaps that we have to overcome in order to achieve a humanoid policy. And those 4 gaps, next, are embodiment gap. So even though humans and humanoids share similar morphology, but their kinematic structure, their dynamic capabilities are still very different. Next. And the second gap, I call a state to action gap. Next. We need to be able to map the poses, proprioception, to the joint torques, right? So this is something that we have to be able to learn. And then also there's the sim to real gap. We need to be able to realize the performance in sim in the real world. And finally, there is also the egocentric vision gap. This is something in computer animation we don't care too much about because we have a lot of privilege. The 3D information is readily available. But in real world, robot has to figure out from its own onboard sensors. So I'm very happy to report that. So I gave this talk 4 months ago at RSS. I'm very happy to report that the first 3 gaps are systematically overcome, especially for locomotion tasks by our recent work. Next. Next. So we have this very robust pipeline now that we start from human motion capture data. We do retargeting to create a robot motion, but this is still just kinematic motion. Those are just poses. And then we train a reinforcement learning policy that turns the poses into joint torque, the physics commands. And then we have this policy roll out and do a real zero-shot sim to real. Next. And this is what we can achieve. Next. This work is called Beyond Mimic. We basically just take a human motion capture and then train an RL policy and put it on robots. And so at this point, I'm pretty confident to say, if you can do a motion capture sequence, I can make it work for robots. And you can see that the motion is very natural and realistic because this is coming directly from human motion. You probably wonder, well, you see a lot of these videos now, right? Like from Twitter, from X, Unitree, a lot of those companies, they put out this kind of videos all the time. What's the difference here? I would say the difference here is that this is not just a video. This is an open source code base, which means that everybody can just start from this. This is a new starting point. You can just directly, if you have a robot, you can directly use the code base and then you can achieve that. And that's what we wanted to do as academics because we want to be able to elevate everybody, not just our lab. Okay, so this is interesting, but every single policy you've seen so far is just a kind of not so intelligent policy because all it does is just to track that one single motion. What we want to do is to be able to track not just a single motion. We want a single policy that tracks any motion. Why do we want to do that? Because if we can track any arbitrary motion, then that means we can build a teleoperation system for humanoid. And this is inspired by a lot of the recent ongoing work from manipulation domain. Training a policy that can track arbitrary poses is a little bit more involved. I will skip the technical part. But once you have that policy, you could actually replace the offline motion with an online motion capture data streamed online from a operator. And then you can achieve something like this. So this is another work called Twist. Here, this robot is being teleoperated. So it's not doing all this motion by itself. There is a puppeteer behind the scene trying to coordinate this robot with the other human. So the intelligence here is a very interesting question. Is the robot really intelligent? Not really. But what the robot is capable of doing is to balance itself. You can give robot a command by doing some kind of motion, but you don't know how robot should balance because you are not robot. And robot has to figure out itself, giving these commands, how do I balance so that I could go out and shopping? Okay, I'm just going to skip that because I have a lot more videos later. Okay, so here you can see the teleoperator. The teleoperator can just do something very free-form and arbitrary and in real time. And robot is able to just follow those poses, but at the same time knowing how to balance itself. Okay, so twist is great. Following the full pose from an operator is something useful for teleoperation. But sometimes we don't want to give the policy the full pose. It's a little bit inconvenient. Oftentimes we want to give a robot just a sparse command, like where your hands need to be, where your head needs to be, which direction you should turn. So we want to be able to have a policy that can just track sparse state. And with that, we were able to create a hierarchical humanoid policy where you can have high-level policy that handle vision and language, and then give out some kind of sparse, like where you should be going, where your head and hands should be. And the low-level policy will realize that into the humanoid full body. And, okay. So this word called head is doing exactly that. So we have a policy that takes as input the position of the head and the orientation of the head, the 60 position of the pose of the head and the hands. And then robot will try to follow that command, but at the same time filling the rest of the body degrees of freedom by itself. So here we show that this is the first frame of what robot sees in its own camera. And then you can point at one pixel and then ask robot to go to that pixel in the real world and touch it. Okay, so that's interesting, but how do we go from tracking full state to sparse state then to any state? Because different application might demand that middle layer, the high level action space differently, right? And I don't want it to dictate what that middle layer should be. And especially right now, I actually don't know what high-level policy is. So I want to be able to have a low-level policy that's very flexible. You can give it to any state that you want to track, and the low-level policy will be able to do that. So we go back to the Beyond Mimic work. We use this RL policy to train a lot of specialized RL policies, and use those policies to generate rollouts. Next. Generate a lot of data, and these data are paired observation and action data. And then you can use that to train a diffusion policy and doing some inference time guidance. This means that, next, you could control the robot by giving any command you want, as long as that command can be formulated as a function of a state, a differentiable function of state. So here we ask the robot to move in certain direction. So basically you can use a joystick control to control robot's direction. And you can also have a guidance saying that don't go to that area, but go to that green area. So you could have this kind of a goal following and avoiding obstacle kind of a scenario. Next, yeah. So here, this is what we show in the real world.
This unified policy can execute new tasks at test time 0 shot.
So what you're seeing here is that this is a combined policy learned from many RL policies. It's a distilled policy, and this distilled policy is actually very flexible.
Simple differentiable cost functions
also very
guide the robot's motion in real time.
Yeah. So next. Next. Yeah. So this is actually a demo I like the most. So here, robot wants to go to the goal, but if you stop the robot is not going to fight you violently. It will actually just listen to you. And the reason robot could do that is because this is a multimodal generative models. So there are many modes that are all, well, the violence turned out to be the human. There are many ways to achieve the goal, and then you can change the goal in real time. All right, so now we have a lot of different kind of trackers that we design. If we embrace the notion of a system 1, system 2, you can say that at this point, we're actually pretty confident that system 1 will have solution. Now we can shift our focus to system 2. So the first question is, what is the input and output of a system 2? I think a lot of people, next, would agree that the input should include at least vision and language. There could be other things you put in there, but those are two input modalities we would love to have. But what is the output? In order to answer that question, we first have to understand how we should train system 2. So there are a lot of choices here. What data should we use to train system? Can we use human data collected in the wild? Or should we just use robot teleoperation data? Or we can use the simulation data from the world models, right? So, just like right now, because the robotics, humanoid robotics is still wide open, we have to put our bets on every single one of them. So we did all of them. So for human data collected in the wild, this is next. A good example is that project I talked about HEAD. We had it before. Next. The vision and right now we're not dealing with the language yet, so vision and the proprioception state. But output of this system 2 should be the next, the hand position and the head position. And we will use that to directly connect to our low-level head RL policy tracker. So how do we train that system 1? The problem statement is, given a goal and a 2D image you perceive, where should you move and where should you look? If you can answer that question, then we have our system 2. So we use area glosses to collect the data. So based on the short history of the videos, we want to predict the head position and head orientation. And turn out that the human data is really, really nice. Next. Because we can predict pretty well, and it catches a lot of those corner cases that would otherwise be really difficult. Next. So for example, when a person approaches a group of people in front of the wearer, it will stop its motion, it will slow down. And when the person approaches a traffic intersection, interestingly, the person will look to the left. And this is something that is very hard to program, right? You have to directly learn from data. And I bet if you use the data from UK, you will get the person looking to the right, because the traffic flows differently. Next. Okay, so with that, we're able to do head, and we can create a system 2 and system 1. There's another way we can do it. Let's use teleoperation. So remember, we have our twist, and we can use this twist. We improve the twist so we don't need to wear the full motion capture suit. And now we can use that to teleoperate and use the data to create a basic VLA. So here is a twist 2. You can see that there's a lot of improvement. First of all, we put a camera on the head, and that camera is on a gimbal, so that means you have additional degrees of freedom to represent the neck. And we also have hands now, so robots can do some basic manipulation. Not very good hands right now, but it's this is improving. And next. All right, so I'm gonna speed this up a little bit, so the robot can do this as the basketball as well. Next. All right, can we skip the next 2 videos? All right. Next one. Okay. Now I also want to show. So I'm gonna skip all of this now. Can we just all jump to the videos, the next videos? So once the robot has a vision, we can start doing really interesting manipulation to entertain our tourists in Stanford campus. All right, next. All right, so what's next? I'm just gonna be 30 seconds. So right now, as you can see, locomotion is very much handled. I wouldn't say solved. I'm resisting to say the word solved, but it's a lot of progress has been done. So the next thing I want to do is to do this again. Next, go back to the cycle again, but this time with manipulation, really manipulation, not just stretching the capability of what we have. Next. Okay, so let's play this video. So here you can see that the robot is capable of manipulating the object and locomotion as well. And doing something quite daunting. All right. All right, final video. Next one. Next one. Next one. Next one. Next one. Okay, I just want to show this one video and I'll be done. Right, so robot manipulation, locomotion has been done, has advanced a lot in the last 3 months. All right, thank you.
Thank you, Professor Liu, and all our international speakers for your brilliant insights and sharing. 那么接下来呢，我们将进入到 panel 环节。出场对谈呢，将会由台湾大学电机工程学系的傅立成特聘教授来担任主持人。那么 AI 呢，正在成为机器人进化的关键力量。不只改变了全球产业的发展方向，也带来了全新的竞争格局。所以呢，接下来这场对谈将从国际趋势出发，进一步的探讨台湾该如何的把握契机，发挥战略角色。那么也相信呢，待会儿的内容一定是精彩可期。那么接下来呢，我们要邀请到今天的语坛贵宾。Next, we move to the panel discussion, moderated by distinguished Professor Li Quanfu from the Department of Electrical Engineering at National Taiwan University. AI is becoming a pivotal force in the evolution of robotics, transforming global industries and introducing new competitive landscapes. So now we anticipate an engaging and insightful session. Now let's invite today's panelists to the stage. First, a warm round of applause for our moderator, distinguished Professor Li Quanfu from National Taiwan University. 欢迎傅教授。And next, let's welcome the following panelists. Let's welcome Professor Tamim Asfour again. Welcome. Let's welcome Professor Atsuo Takanishi. Welcome. Let's welcome Dr. Stan Birchfield. And next, let's welcome Professor Karen Liu. Welcome. 那接下来我们把时间交给傅教授。
Okay, good afternoon, ladies and gentlemen, and distinguished guests, speakers. It's really a true honor to be here with this full, really expert, robot experts. So today I'm going to have this last sessions with panels, and after this so exciting talks. So I'm sure that they have a lot of words they want to say besides what just presented. So before I start giving them some questions so that they can share their wisdom, I think over the past decades, we have already experienced a remarkable journey in AI developments, witnessing the rapid evolution from predictive AI, generative AI to the eras of physical AIs. In this panels, all the panelists are the real experts of robotics, but we all collectively recognize that profoundly this AI. We recognize how profoundly AI has empowered service robotics. On unprecedented scale. And the pace of recent advancement is truly extraordinary, leading us to believe that such AI-driven humanoid robots with certain degree of autonomy may soon become part of our everyday lives. So of course, we also understand that a humanoid robot is not a humanized robot. So while achieving the latter ones, not only we need perception, but also we need cognitions, such as the ability to feel, to reasons, and respond with understanding. In other words, there's still substantial room for research and development for us to realize these visions. Okay, so I think this is something I feel that this is also some remark I can share with everybody here. So in the following, I would like to I already prepared some questions, but some may be already answered by the speakers, but still, I believe that some you might be able to add to the questions. So I noticed that almost 3 speakers addressed the humanoid robots, but I'm sure that the purpose of having this future tech, especially our governments, want to know your visions about the AI-driven robotics. So my first questions, if you, the questions are on the papers. The question is, could you share your perspective on the developments of AI-empowered robots over the next 5 to 10 years? Okay, and also provides an approximate breakdown of the different types of general-purpose robots currently in the field based on your own classification or standard. So this is my first question to all the speakers. So if you are willing to address these questions, yeah, please feel free to do it. So who want to start with these questions? Yeah. Yes, please.
Maybe I can start. Yeah. Yeah, as you mentioned and mentioned by the speakers today, we made really progress in the last years, thanks to advancements in many areas. Better actuation, 3D printing, PCBs, more compute resources, but also thanks to AI, to progress in AI. Many of the computer vision tasks we're dealing with in the last decades are now solved. So foundation pose, foundation stereo, and many others vision models, which solved hardcore problems in computer vision. And I think this will continue. I mean, we see now that we can implement more versatile tasks with robots than in the past. I mean, look at the examples what Professor Lu showed today with whole body motion, in particular locomotion, yeah? And the next step would be to combine that with manipulation, for example. So I think, yeah, AI is helping us, but AI and in particular data-driven approaches will not be, and this is my opinion, the solution for robotics. Yeah, I think we have to solve the hard problems, and one of the hardest problem in robotics is manipulation, and this is very important. If we manage to achieve the same level of progress as we did in locomotion now in manipulation, I think we'll have fantastic applications and use cases for AI-powered service robotics everywhere, not only humanoids. Yeah, I think in the next years we will have more robots applied in still structured environments or well-defined applications. And maybe in 10 to 15 years, we can talk about robots which can do professional healthcare and general purpose humanoids which can perform any task, maybe not any task, but many tasks of what humans can do. Yeah.
Fantastic. Yeah. Anyone else would like to share?
Yeah,
Parents?
I can add to that. Is it on?
Yes.
Okay. Agree. Yeah, that the next challenge is really combine locomotion, whole body manipulation with dexterous manipulation, and also navigation. To me, the hardest question is the how do you combine it, right? There, just from what we're doing here, there are a lot of choices, and it's really hard to predict what this system or high-level policy will do, so that we can prepare our low-level policy to be able to handle this interface in the middle. But I think that this problem will be solved. You are asking about 5 to 10 years. I think this problem will be solved next year. Just the combination of that. But there is a really big problem right now. We don't have a good hardware that has good whole body and good dexterous hands. People are improvising things right now, right? Just because, you put a really complex, heavy hands on a robot, a humanoid robot, it overheats the joints, overheats the motor right away. So there's just a lot of fundamental hardware problems that we don't have a good grasp yet. And I think once the hardware is there, software will catch up immediately.
Great. Okay, anyone else? You want to add?
Yeah, I fully agree, actually, that we still have a lot of problems in hardware development. I mean, we have to understand how to really engineer the systems from mechatronics point of view, to have systems with human-like performance, for example, in terms of torques and payload and so on. But I don't agree that the software will just be an add-on. I think we have to really develop the two things together. I think this is really important for the future, that we think about robot systems not as separation of hardware and software, but really as a joint system where software will or hardware can maybe make software easier and software and vice versa. Yeah.
Mm-hmm. Okay, fantastic. How about the awareness? Awareness for the environments in the next 5-10 years, how that will go so that this robotics can go even deeper into our life or to any service sectors?
Yeah, I can address that. So I think the big bottleneck, as we all know, is training data, right? So in robotics, we're way behind other fields in training data. And there's still an open question about whether we need more real data or synthetic data, whether the real data needs to be teleoperated with, annotated with actions, or whether we can use actionless data with online videos and that sort of thing. So I think this is still an open problem. And I guess the question of when will we get there, or I see it more of as an incremental progress, where we start with a set of well-defined tasks, we have training data for those tasks, and then we iterate until we can declare success on those tasks, and then generalize to new tasks. I guess I'm maybe not as optimistic that we'll be able to solve like a wide range of tasks in 1 year, let's say, right? But we're making good progress, and I think that'll continue.
Okay, fantastic. Takanishi Sensei.
To me, finding of users is the most important thing in the market. If the humanoids are so useful for them, they are willing to pay the money for us. Don't you think so? The one big application, I didn't have time to show you the video, but I worked with several medical person working together with Kyoto Kagaku. They are building a sort of robotics human patient simulator. So human and robot is very useful to simulate many different types of human disease. So especially for medical doctors or nurses, they have no time to learn many different types of technique in medicine. Nowadays, they are using real patient. It's so dangerous for me because in 2010, I had a heart surgery. So I needed to believe them that they are skilled enough for my heart. So anyway, humanoids can be useful for skilling up those people, because you can anytime you can fail, because it's a robot, but mimics many different types of symptoms, many different types of diseases. So it's one big market for, I believe. Mm-hmm. Yeah, and disaster cases. Now Japan has a big tsunami, big earthquakes, and a volcano eruption. Many things are happening. So how do we protect our society? And also every year, many firefighters are dying. So this is a big direction for me to go to the disaster-capable robotics. Mm-hmm. Not only humanoid, but those technologies will be useful, I believe.
Okay. Talking about the users, so it will be related to the service areas. Recently, Elon Musk predicting that they are going to produce like 10,000 Optimus in a year or two. I don't know. They are saying that making the human robot originally is our daily research that we make for example, Professor Asfour, you made Generation 7, right? So that time we're working on the research and start also at the same time we are looking for potential users. And healthcare definitely is one. But now since people are developing all this and looking at the 30 million working forces in the world, and they use this as an estimate and try to justify the future potential profits of making these humanoid robots. I'm not sure whether the speaker, do you agree with this, that in the futures, maybe these human robots not necessarily coming into the healthcare sector, maybe into the manufacturing or working sectors as Jensen Wang's or they predicted. How do you see that they're trying to make up the potential shortage of the working forces in the world in the next 5-10 years? How do you look at this? Can you express your ideas or your wisdom about this?
Yeah, I mean, we need technology, right? I mean, we need more automation in the society in general, everywhere. We have labor shortage, we have demographic change, and I don't think we have, and automation through robotics, humanoid robotics is one solution, yeah? But as you mentioned also, I don't think that only healthcare is or healthcare is the only application of humanoids. Humanoids should be able to do any job what a human can do, also in production. It will be a huge market for humanoids, yeah? I mean, people like Musk and others, they really can analyze the markets and so on, and this is a big vision, and it will be a big market. But I want to see it first. It will take time. And I haven't seen actually things working in real. I saw only videos, and we have to be careful about the gap between videos and reality, unfortunately. But I am a very optimistic person, and I wish tomorrow or in 2 years we'll have humanoids which can help in nursing homes, in production, everywhere where in decontamination. But I think the problems are harder than what many people are claiming. Yeah. But at some point, if we solve manipulation, I think we will have these systems.
Okay. Anyone would like to share your views about
By the way, I have a question that any manipulator that can tie shoelaces, anyone realized before? So your shoelaces, can you do that by yourself? Yes, human can do it, even small kids. But
Robots
how
can
about
do
the
that.
manipulator?
Robots. I don't know if you follow the Aloha robots, teleoperation. They train the robots. They collect a lot of data from human demonstration. Tying shoelaces is one of them, and they train a generative model to be able to tie shoelaces. So yeah, it's happening.
It's happening?
Mhm.
Oh, really?
I'll show you the video, but it's a video. Yeah. Yeah, I mean, I seen that, the demo, you know, it's probably not as 100%, but they got a pretty good, you know, I don't know the percentage, but it definitely is capable of doing that, but not always.
The beginning stage is separated, the laces are separated from shoe itself?
No, well, the laces are already kind of threaded into the shoes,
yeah.
but they basically make a knot.
So there are a lot of skill should be needed for even for that simple purpose. That might.
So maybe it still takes out some time, right?
Yeah, actually, I mean, in humanoids there are so many big problems what nobody is talking about. I mean, think about the humanoids in a retirement home or in healthcare or even in production. I mean, we need a certification for this humanoid. I mean, this is not just a machine which is, in particular in healthcare. I mean, there are safety regulations which must be addressed. And I mean, maybe some people started now thinking about safety of humanoids. And the other thing is, I don't think the solution will be we need more data, we need more compute. So if we think about humans, I mean, we are very resource-aware systems. Our brain survives with few watts per day, right? Mm-hmm. And if we have a humanoid with 2 GPUs, whatever, I don't know how many kilowatts per day we would need, yeah, and how heavy the batteries will be, and so on. I mean, so many details, but are important. I mean, if we are claiming these robots will be at home or in production lines, we have to solve these problems too. And unfortunately, I mean, maybe we have two lines or directions in research. Some people are claiming with data and more compute we will solve every problem. I doubt that this will be the solution. And other people may be trying to combine model-based approaches with data-driven methods so that we have the best of both worlds. But the safety issue in humanoids, energy consumption, are crucial and must be addressed before talking about introduction of this technology into any serious application.
Fantastic. Okay.
Yeah, I'll just add one thing, which is in agreement with you, Tamim, that it's tempting to sort of fall into one extreme or the other, right? So one extreme is that they're like, we're almost there, and the opposite extreme is that we'll never get there, or it's going to take a lifetime. And I think the truth is probably somewhere in between, right? There are a lot of unsolved challenges. We don't know exactly how to solve these hard problems, and a lot of research is needed. And it's really anybody's guess as to how long it's going to take for these things. And so it is, I think we just have to sort of chart a course forward that takes into account, like you said, safety and so forth. And then there's also a gap between solving the technical challenges and then on the one hand, and then solving the economic challenges on the other, right? To make it economically viable, we have to have hardware that's reliable and cost efficient and so forth. When it breaks, you can repair it quickly and easily, or it doesn't break and that sort of thing. So just a lot of questions on many fronts that need to be solved.
Okay, great. Anyone want to add anything else? Okay, if not, then this question is for our governments. So, what role do you think Taiwan can play in advancing the development of AI-empowered robots? And how can we further promote our industries to contribute meaningfully to society and the global communities? So if you think what could be deficient at the moment, but the policymaker, such as our governments, or you just imagine if yourself is a policymaker in your countries or organizations, what do you think is what we can do further to strengthen our chances to be better than the others? Can you share your wisdoms? Yeah, this is for, I think, our government definitely is willing to listen to any of your suggestions, yeah.
This is clear, right? This is clear, right? I mean, you have to build on the strengths of Taiwan, right? And Taiwan is the place where semiconductor industry is worldwide leading, and you have to make a point out of it, yeah, to develop key technologies for AI-based robotics, where these components for AI algorithms, for communication, for control, for learning, is maybe implemented in hardware. Yeah, this is one strength of Taiwan. I think you should keep in mind. I mean, we get asked the same questions in Germany. You know, this is, and one important thing I would like to emphasize, actually, when it comes to strengthening industry and transfer of our research to industry. I don't have a concept actually how we can accelerate transfer from research into reality. This is a huge and big topic, but we shouldn't forget that basic research is crucial and important, and we cannot only talk about transfer. We have to keep promoting and supporting basic research, because this is the source for transfer. And maybe we have something to transfer now because we invested a lot in basic research in the past. So, and therefore my recommendation, don't forget about basic research. This is the origin where results are generated which we can transfer. And this is where we educate the next generation and talents to develop the next technologies for Taiwan, Germany, for the countries. Yeah.
Okay, great, thank you. Anyone, Karen?
There's a long term and short term, right? Short term, it's also not too short, but it's more immediate. I think Taiwan should do what NVIDIA is doing, basically compete with NVIDIA. I'm not really meaning competing with it, but you just look at it, their grand vision. They want to own this entire stack from the hardware all the way to the AI, like at the top of it. And I think Taiwan has a chance to do that too. And NVIDIA has a really good roadmap already in front of it. So this is more short term, but in the long term, I totally agree with you, Tamim. The talent pipeline is so important. Like one thing where at Stanford, the most important thing to me is recruiting the best talent. And once you get them to the right place, given them the environment, they will do amazing things. So where is the pipeline in Taiwan for robotics and AI? I think that's where I would start thinking about.
Okay, great, thank you. Stan, or okay, maybe Stan first. Yeah.
I don't know what I can add to that. I mean, basic research is absolutely crucial. 100% agree. And so going forward, Taiwan should build on its strengths, right? You've got so much talent here, right, and so much expertise. in semiconductors and especially, of course, and then also in just tech fields in general, that building on that strength, encouraging students to go into these areas, providing an environment in which they can thrive in inventing new technology, fostering startup companies, and so assisting existing companies as well as new ones is crucial. So, yeah, I think that's where the focus needs to be. Yeah.
Okay, thank you. Takanishi Sensei.
Yeah, that's a very difficult question for me. But I am also the president of a Japanese society called Workload Users Association. That's not the technological side association, but the users association robotics. So always you need to find the users if you want to extend your technology or commercialize your technology. So users is the most important thing for me to accelerate the current technology. So anyone who visited many factories in Taiwan to see, to understand what the problem of them and which direction is needed for Taiwanese companies or something. Mm-hmm. That's my opinion.
Okay. Yeah. So as a matter of fact, Taiwan is known to be very strong is the supply chain. We actually have a very strong supply chain, of course, semiconductor as well. But today, from all the speakers, it seems that our NSTC seems to also support that fundamental research basic research is really, really important. Because if we don't do now, maybe 5 years, 10 years later, we are short in that, right? So I think we not only leverage what we have, but we should not forget the fundamental research, what we should put our focus on, right? Tammy, you want to add maybe just one last?
Yeah, it's actually not only the basic research, it's the entire ecosystem which combines basic research, talents, and innovation. And I think these three things must go hand in hand. Basic research, talent, generation of the next pipeline of talents, and innovation and transfer. And these three things are important, and this is a very difficult equation. How you make progress? Actually, nobody knows that. All countries, Europe is talking about this famous ecosystem which integrates basic research, innovation, and talent generation. But there are no solutions yet. I mean, this is something what also Taiwan should think about. But yeah.
Okay, great, fantastic. I think time is up. So thank for today's wonderful. So please join me to thank all these wonderful our panelists. Okay, give them a big applause. Thank you.
Thank you for the wonderful panel. 我们再次的感谢我们的贵宾。Please stay a moment. We will take a group photo. Okay, please look at the central camera. Please stand up for the photo. Please. Okay. Okay, and one more photo for stand up to the camera. Yeah. Together? Yes. Okay, and one more thumb up gesture. Thank you. Yeah. Thank you. Once again, thank you, our distinguished guest. And 非常感谢各位贵宾，大家今天热情参与，我们也感谢我们的讲者们为我们带来非常前瞻的视野跟深刻的洞察。相信呢，大家呢现场都有激发更多的思考跟合作契机。Ladies and gentlemen, thank you for your participation. And we extend our gratitude to the speakers for providing profound insights. Also, we believe today's sharing will inspire further thoughts and collaboration opportunities. Once again, thank you for your participation and have a nice day.